Hi class, I wanted to explain this idea a little bit more thoroughly that came about in the second video in Chapter 16, kind of the middle part of Chapter 16, where we were talking about the life cycle of a protostar and how at some point in the development of this protostar, the surface temperature remains at about 3000 Kelvin while the star shrinks a little bit, it contracts a little bit. And the idea, kind of the reason behind why the star maintains that temperature at the surface for a little while had to do with how energy was moving around inside the star. And so the book talks about, and I mentioned a little bit in the video, and we'll talk more about this in the next chapter, this idea between convective versus radiative transport of energy. So this idea of convection versus radiation and how energy moves through the star. We want to try to understand that a little bit better, and this will be something we'll see more of in Chapter 17. So we just kind of going back a little bit from earlier things, we remember that atoms are systems of particles that are bound together. For example, proton and electron. That's what a hydrogen atom is. They're bonded together by the electromagnetic force. Other atoms as well, helium, all the other atoms are nuclei bonded to electrons. So it's a bound system. And so you can put energy into that bound system. You can try to make the electron, in a sense, move further away from the nucleus by giving it extra energy. And so that's the way that an atom can absorb energy internally. We can add internal energy to an atom by either shining light on it. We can shine light on the atom, and if the light has just the right energy, the atom will absorb it. Or we can make the atom collide with something. So we can collide it with a wall, we can collide it with another atom, we can collide it with a molecule. And the energy of that collision, the kinetic energy that those two particles come in with, that some of that energy can be used can be transformed into internal energy of one of the things, the atom or the molecule. And we talked about how that is a process that is going on inside these protostars as they're first forming to help keep the cloud kind of cool. The molecules absorb energy and then they re-emit the energy in the form of light. So this is something we hopefully know and kind of understand by now, that atoms can absorb energy and the energy turns into some kind of internal energy. And when the temperature is low, think about a low temperature gas, atoms and molecules that are colliding at low temperature, they're not moving very fast. So the collisions are not very energetic. And there might not be enough energy to totally ionize the atom, but rather you could just simply increase the internal energy of the atom. Still keeping it a bound atom, the electron is still bound to the nucleus, but you've just added a little bit of extra energy internally. So we say that the atom has been excited. But at higher temperatures, the collisions could be more violent, and the atoms can actually be ionized. The electrons can be knocked completely out of the atom. In other words, you can completely unbind the atom, tear it apart if you have enough energy. So again, high temperature means you can ionize gas. Low temperature means you can't ionize the gas, but you can at least excite the atoms. And once they are excited, they then give off the energy in the form of light often. So this is a diagram we saw back in Chapter 5. And this is important. This is just a general kind of idea of how things change as we go through different temperatures. And just remember that at low temperatures, things can be solids. And this is examples. This is an example of water. So this is ice, water ice. These are water molecules. At higher temperature, it turns into a liquid. At even higher temperature, it turns into a gas or a vapor. They're still molecules, but they're flying around more rapidly. At even higher temperature, you can start dissociating the molecule. You can start taking the oxygen and the hydrogen atoms apart. And you're not necessarily taking the atoms apart, but you're taking the molecule apart. So it's molecular dissociation. At even higher temperature, now you can start taking the atoms apart. You can start removing electrons from the atoms, and you're left with a positively charged atom that might still have electrons bounded to it, just depending on how many electrons it started with. But you'll have electrons, free electrons kind of flying around, as well as ions, positively charged atoms, which is nuclei, flying around as well. At even higher temperature, you can remove all the electrons of an atom. And so at the really, really high temperatures that we find in the cores of stars, everything is totally ionized. It's just a swarm of electrons and nuclei, positively charged nuclei and negatively charged electrons. So this is just the kind of the patterns we've been talking about how temperature changes things, changes the state of matter. So going back to a little animation here, there's, again, this comes from that site, that PHET site, just to kind of remind you, this is a model, a very crude model of the hydrogen atom, having the nucleus in the center and circular orbits of the electron around the nucleus. This model doesn't, there are certain things it cannot explain, so it's not a good model. There are better models for how hydrogen works, but it's good enough just to demonstrate this, again, this idea that atoms can absorb certain specific energies. In fact, all that we really care about right now is the fact that atoms can actually absorb light energy and collision energy. So what we're going to do here is we're going to shine white light with this laser gun onto a box of hydrogen gas, and this image is we're kind of peeking inside this box, looking at a hydrogen atom. So this is the proton, this is the electron, and when the hydrogen atom is in its happiest, lowest energy state, the hydrogen atom is kind of, in a sense, the electron is sort of, in a sense, orbiting in its smallest radius. Again, this is not a good model. It was one of the initial models of hydrogen that did explain some things, but there are some things that it doesn't explain. But it's good enough for our purposes right now. So let's turn this gun on, and you'll see a bunch of different colored things passing by here, and those are just different colors of photons, different colors of light. And you'll see that occasionally one of them will get absorbed by the atom, and that electron will pop out somewhere else on a different circle. And then eventually the atom will relax, it'll give up that energy, and you'll see a photon kind of travel off in sort of a random direction. So let's just watch and see what happens. So we start this, and there goes all of our light. Oh, there goes the electron. It goes up there, and it's orbiting around. And now let's see if it absorbs something. Oh, there it goes again. It absorbed, oh, and it emitted something. So you can see how the atom will absorb certain colors and emit other colors. It'll absorb certain colors and emit either the same color or certain colors related to these different energy differences. So remember, we talked about an energy level diagram. The lowest energy state is what we call the ground state, and see it jumped up now to a higher state, and as it comes back down it can lose energy and give off light. So that's the absorption and the emission that atoms can do. So going back to this idea of convective transport then means that at low temperature, because the atoms can absorb energy, the atoms will absorb light energy, and when they do that, that light energy will will make the gas hotter, make the gas warmer. With a warmer gas, because it's absorbed this light energy, it will rise. The gas will normally expand, and as it expands, it becomes less dense. And when it becomes less dense, it rises. It goes up. It goes against gravity and rises. And so the gas rises, and ultimately it'll lose its extra energy at the surface of the star, when that energy is then turned into the form of light energy. And so convection again is when the temperature, convection happens again when the temperature is not too high, so that the gas can still be atoms with electrons around them, and not just ions. And those atoms can absorb light energy. That energy kind of gets trapped inside the atoms. The atoms travel upward, in a sense, away from the center of the star, and they ultimately lose their energy at higher levels near the surface. They emit the energy in the form of light. Radiative transport, though, is something that happens at higher temperatures. So when the temperature is high in a gas, remember the atoms can be ionized. Either just maybe one electron's removed, or maybe a bunch of electrons are removed, but you can have atoms being ionized. And when they're ionized, they can't absorb the energy anymore. They can't absorb that energy that they used to absorb. And so what happens to the light is it basically just hits the charged particles and kind of just bounces off of them and goes off in random directions, but it doesn't necessarily get absorbed. The energy doesn't get trapped inside the atom. It gets just kind of scattered and sent off in a different direction. So when the temperature is high, light can travel through the gas without getting absorbed, but it does take kind of a random path, kind of bounces around. So that's the idea of radiative transport. Light is still light. The energy is still in the form of light, but it's just traveling through the gas, bouncing off of things, and eventually making its way outward. And again, convective transport is when light can actually get absorbed, and that's when the gas is at a lower temperature, so that it's still not ionized, and the light energy can get absorbed, turns into thermal energy, the gas gets hotter, and the gas expands and rises up and releases the energy when it's higher or further away from the center. So in protostars, as we talked about, as a protostar forms, at first it's fairly cool. The temperature will gradually rise, but while it's less than about 3,000 Kelvin, all those atoms are not ionized. and so the energy thus flows through convection. So when you have a gas of atoms and nothing's ionized, the energy is going to flow primarily through convection. The atoms are going to absorb energy and warm up, and that warmer gas is going to rise and eventually give off its energy near the top. Temperature is always hotter near the center of one of these things, cooler at the surface. So if the surface then when the surface is about 3,000 Kelvin, the surface then is just totally unionized gas. It might be a little hotter underneath, and so those warmer layers might have some those warmer layers beneath the surface might have some ionized hydrogen. Not all of it will be ionized, maybe some of it will be ionized. So you'll have kind of at the lower levels, the lower layers where the temperature is a little bit above 3,000 Kelvin, you'll have some regular hydrogen and you'll have some hydrogen ions, some basically just protons and some free electrons flying around. Those electrons that were removed from the hydrogen atoms can do one of two things. They can either recombine with a proton to form a neutral hydrogen atom, or they can actually combine with an already neutral hydrogen atom to create a negative hydrogen ion, an H-. And H- is a very weak kind of bond. It's a proton with 2 electrons going around it. It's still a hydrogen atom, but it's got an extra negative charge. It's got an extra electron. And it turns out that these negative ions, these hydrogen ions, are really good at absorbing a lot of visible light photons. So once you have these hydrogen ions formed just a little below the surface where the temperatures are a little bit higher, they'll absorb a lot of light. They'll cause the energy then to be absorbed and then to flow to the surface through convection. The gas will get warmer and then the gas will rise, and it'll kind of, in a sense, trap that energy within the gas, and it'll release it at the surface. So it'll release the visible light sort of energy at the surface, and where the temperature then has gone down to about 3,000 Kelvin, where the atoms are not ionized anymore. And then the energy reaches the surface and then is radiated into space. So it doesn't actually reach the surface and warm the gas at the surface. It reaches the surface in these hydrogen ions and leaves the surface without warming the gas. And so for a while the temperatures aren't too hot inside the protostar, so there's still some neutral hydrogen, the surface temperature remains at about 3,000 Kelvin. So and gravity will keep squeezing the star. So the surface remains at about 3,000 Kelvin, but the star itself becomes a little smaller and a little smaller. Thus its luminosity decreases. Again, because the interior is a little bit warmer than 3,000, we've got these negative hydrogen ions, and they, in a sense, don't allow that visible light to reach the surface to warm the surface. Instead, what they do is they absorb that visible light below the surface, carry the energy upward, and release it at the surface. And so, in a sense, it keeps the surface, those negative hydrogen ions keep the surface from getting warmer than about 3,000 Kelvin. Eventually, though, the interior continues to get hot because the star is contracting. Eventually, we get it hot enough that nearly all of the hydrogen gets ionized, and we can't form those negative ions anymore. And so the absorption of light won't happen. And so it is then able to reach the surface and warm the surface. And then the surface does get warmer, and the star does start actually getting brighter, and it does actually start expanding a little bit. And so this explains, basically then we're switching from more of a convective transport of energy inside to a radiative transport of energy inside as the temperature gets higher. So again, this explains this figure from the second part of Chapter 16, where the protostar gradually gets brighter and warmer, but then suddenly the temperatures are just such that about 3,000 Kelvin at the surface, the star continues to shrink, but the temperature remains constant. So this is when there's convection inside the star, and convection is carrying energy to the surface and letting that energy escape without warming the surface. And so the star remains at about 3,000 Kelvin, roughly. Maybe it increases a little bit, but roughly about the constant temperature. But the luminosity definitely goes down because the size of the star is shrinking. And then once the temperature gets high enough inside so that nearly everything is ionized inside the star, then radiation can travel more freely in the star, and you have what we call radiative transport primarily in the star. And then that allows energy to make it to the surface and actually warm the surface. So the temperature now starts to increase and the luminosity starts to increase. And then eventually fusion starts, nuclear fusion ultimately begins, and the star settles down into an equilibrium position on the main sequence. So that, hopefully that explains it a little bit better, maybe, maybe not. It's not an easy concept to understand. If you really want to get into the details, here is an article, a little chapter from a book on energy transport in stellar interiors. This is a subject, I'm trying to explain it in simple terms. It isn't easy, but it's a subject that is pretty complicated, and there's aspects of it that astronomers still don't understand. Just kind of scrolling through this document, you can see that it becomes pretty mathematical pretty quickly. And if you are interested in any of this, which maybe you are, maybe you're not, you don't have to worry about it, but you can see that as you scroll through some of this, it gets pretty crazy as to the kind of mathematics they're using to try to explain what's going on inside of stars. So these systems are very complex. There are aspects of them that we don't completely understand, and there are things that we understand fairly well. But it takes some pretty heavy-duty mathematics to explain things ultimately, and so trying to explain things in simple terms, doesn't always make perfect sense. You might think in your head that maybe you might have some questions about, well, what about this, what about that? Well, that's ultimately explained through a more mathematical model that we just don't have the time or the energy at this point to get into. But this is something, if you're ever interested in the more mathematical side of things, it's definitely something you could do, in a kind of an upper undergraduate level astronomy course. So thank you for watching, and we'll see you next time.